1 minute. Yes. Can you please confirm my presentation is visible? Yes or no?
Yes, sir. Visible, sir.
Okay. Okay. Thank you so much for the confirmation. So today is the 11th class and 2nd July and unit number 3, that is a battery energy storage system. So in the previous class we discussed functionality of the BMS, that is a battery management system, architecture of the BMS, challenges in the BMS, and future trends in the BMS development. So is there any confusion, any query related to BMS? So in the last class we discussed the what is a BMS and overall architecture and what type of parameter we have to study and we have to analysis and what is the function of the BMS. So overall structure in the previous class we already discussed. So there is like theoretical discussion, correct? So today we are going to see a few numerical as well as the remaining topic. Okay. So today we are going to discuss the battery spec sensing. So what type of parameter we have to sense? So there is a current, voltage, and temperature. There is a major parameter. Isolation and thermal control we have to control. There is isolation as well as a thermal control, and then we will see the numerical of the battery parameters, correct? So we have to calculate the SOC and other type of parameters. So today we are going to discuss these three topics. So we can set two topics and third one, there is a numerical part. So battery pack sensing, there is a current and voltage, because current and voltage there is a most important part, and then we can say the temperature. So why sensing is important? So accurate monitoring, that is accurate monitoring sensing of the battery pack is essential for the safe and efficient operation. So why we have to sense the all these parameters? So we have to measure the all the parameters to safety of the battery as well as the high efficiency. So we will get the like high efficiency by sensing this type of parameter, especially in the applications like the electric vehicles, energy storage system, and industrial application, industrial battery, correct? These sensing parameters are core to the any battery management system. So this parameter means there is a voltage, current, temperature, SOC, depth of discharge, correct, power. So many parameter we have to sense. Okay, so how we can sense the current and voltage as well as temperature, this is the most important part. So current sensing, purpose of the current sensing is to monitor the charge and discharge the current flowing in and out to the battery. So why we have to sense the battery current, correct? So we have to see the how much percentage of current is there, correct? Estimate the state of the charge. So we have to estimate the SOC. Detect the overcurrent, short circuit, and the fault condition. So we will discuss this thing in the last unit. So there is a condition monitoring. Okay, so we have to detect the overcurrent, short circuit current, and fault condition. Track the battery use history. Correct. So that's why we have to sense the current. Common method, there is a shunt resistor plus differential amplifier. So normally we use the shunt resistor as well as the differential amplifier to measure the current. Measure voltage drop across the non-low value resistor and accurate cost effectively. So Hall effect sensor also we can use the Hall effect sensor. So measure the magnetic field induced by the current, and then we can say current value is like this, correct? So normally we can use the Hall effect sensor. Provide the galvanic isolation suitable for the high current. So normally we can provide the galvanic isolation suitable for the high current. Suppose your battery is a very high current, then we have to provide the isolation. And which isolation? Normally people prefer the galvanic isolation. Apart from the galvanic isolation, another isolation is also available, but low cost and like good efficiency, galvanic isolation is very good. Current transformer, yes, most of the student working in the electricity authority board, so they must know about the current transformer and voltage transformer, CT and PT. So use the AC or pulse DC system, not suitable for the low DC current. So normally we can use the CT and PT for the high current and high voltage application respectively. Okay. So most of the student know about the operation and working principle of the CT as well as the PT. Normally we use the PT for the measurement of the voltage, and normally we can use the CT for measurement of the current. Voltage sensing purpose. What is the purpose? To monitor the individual cell voltage and overall peak voltage. Correct. So we have to measure the individual cell voltage as well as the overall peak voltage. Detect the over voltage and under voltage. There is the most important part, because suppose voltage is over voltage, so maybe that it is a blast, and suppose voltage is under voltage, so it will not working properly, because minimum voltage is required for the cell. Correct. So that's why it is the most important part. Just 1 minute. Yeah. So we have to measure over voltage and under voltage, manage the cell balancing, because cell balancing, that is the most important part, and estimate the SOC as well as the state of the health. SOH is nothing but state of the health, and SOC, that is a state of the charge. Okay. Implementation, each cell is connected to the ADC. ADC is nothing but analog to digital converter. Input via voltage divider, also isolator. Correct. So because we have to measure the voltage, so we can use the voltage divider, otherwise the isolator. High voltage isolation, example the opto isolator or isolation amplifier, may be used for the multiple cell pack. Temperature sensing, prevent the overheating which can lead to the thermal runaway. So there is a most important part. In the beginning of the class, even beginning of this unit, I told measure the temperature is the most important parameter nowadays. Correct. So we have to maintain the minimum range of the temperature, optimize the charging and discharging rate, and enable the thermal management control. So this type of parameter we have to continue manage, and we have to continue monitor. So we can say our battery management system is very good, and it will give the very good result also. Which type of sensor we can use for the temperature monitoring? So normally we can use the NTC thermistor. So normally there is a type of the thermistor. So many type of thermistor available. Negative temperature control, positive temperature control thermistor. So NTC stand on negative temperature control. Correct. Otherwise the negative temperature coefficient. And another one is a positive temperature coefficient. Okay. So thermistor is a device to measure the temperature, most common, cheap and non-linear device. Okay, so we can use the negative temperature coefficient as well as the positive temperature coefficient. RTDS, there is a like register temperature dependent. Correct. So one more component, there is a register temperature dependent. There is a PT 100. There is a one type of RTD serial number, higher accuracy and the stable. So suppose you want the higher accuracy, then we can use the RTD. Okay. Semiconductor sensor, suppose IC base, that is integrated circuit base, we can use to measure the temperature, because linear output, digital options available. So suppose you want to use the semiconductor material, then we have a digital options are there. Placement, so where we have to place this type of sensor. So sensor are placed on the cell surface, between the cell, or in cooling channel for accurate heat mapping. So maybe you can place on the cell surface, maybe between the cell, yeah, maybe in cooling channel for accurate mapping. Okay, so this type of sensor you can use to measure the temperature. Now, next one, there is a battery pack isolation. Why isolation is required and what is isolation? Okay, so isolation meaning, that is a simple meaning. Isolation means we have to separate the two devices, maybe the two cell, maybe the two devices, anything. So suppose we have a panel 1 and we have a panel 2, so we have to divide both panel, so we have to isolate the both panel. So electrical isolation is a critical for safety and protection in high voltage battery pack, because that is a high voltage means high current, so it is a very risk. So but we have to isolate all the cell. Example, more than 48 volt typically in the EV and the solar storage. Correct. Why isolation is needed? Prevent the ground loops and accident shock. Somewhere we can sense the shock from the battery, so isolation is most important. Protect the low voltage control circuit from high voltage battery section. Correct. Ensure the communication safety between the BMS, that is the battery management system, charger, motor controller, and vehicle system. Because BMS connected with the motor as well as the auxiliary supply, everywhere that is a connected. So we have to make sure that is a proper isolation must be there. Battery pack sensing, there is a temperature. So thermal control of the battery management system. Thermal control ensure the battery operate within it is a safe temperature range, typically 15 to 45 degree for the lithium ion. So this range for the lithium ion only. Why it is a matters? Prevent the thermal runaway, there is a safety hazard. Improve the battery life, that is the most important, and maintain the performance and the capacity. Enable the fast charging without overheating. So that's why we have to measure the temperature and continue monitoring the temperature. Okay. So summary form, we can say thermal management method, there is a air cooling, liquid cooling, phase change material. So air cooling is what? So force or passive airflow. So we have to flow the air. So there is a air cooling. Liquid cooling, circulation of the coolant through the cold plates. So there is a liquid cooling. Phase change material, absorb the exit heat passively. So normally used in small EV and UPS, that is air cooling. Liquid cooling normally use EV and e-buses, and phase change material, there is a battery modules. Okay, so these are the like temperature sensing method. Otherwise, we can say the thermal management method.
Sir, what is sir liquid cooling?
Liquid cooling means we have to give the liquid. So, do you know the liquid heater? Do you have any idea about the like oil heater? So normally we use the heater in the during the like winter season, air heat, oil heater. So what is that? So normally we have a tank like this tank, and inside the tank. So suppose this is the tank. Inside the tank, liquid is there. So this is a flow. Do you know radiator in the vehicle? Radiator is there.
Yeah, heat radiator. Yes.
Yeah, there is a same thing. In the
The
in
same
the in
inside.
the radiator, we can put the water. Correct. We can insert the water, and water is a liquid. So there is a same material. So you can see the circulation of the coolant through the cold plate. So you can consider this is the plate, and we can put the maybe the oil, maybe the any material, maybe the water, any material. So for the like manage the temperature, maybe the mixing of the any liquid. Correct. Got it? Yeah, still confusion.
Yes, sir.
correct. So it is the same like radiator, so what we can use in the vehicle, correct. Otherwise maybe you can see the oil heater. In the oil heater it is the same plate is there. In the inside the plate we have to put the oil, and once we pass the current, so oil will heat, and we can get the hot air from the oil heater. So same like in the liquid cooling, so we can get the cool. So that is a mixing of the many material, many liquid, and that is a circulate in the plate. Got it?
Yes.
Any other confusion? Any other query?
No, sir.
Okay, thank you. So integration of the BMS integration. So we have to integrate each and every components. So temperature sensor feed the data to the BMS. So whatever data we can get from the temperature sensor, so that we can feed to the BMS, because BMS is nothing but your management system, correct? Battery management system. BMS triggers the cooling fan, pump, and heaters. So based on your requirement, based on the customer requirement, maybe sometime there is we can start the cooler, sometime maybe we can start the heater, correct? Sometime maybe we can use the pumps. So that BMS is trigger as per the customer demand, correct? So we can press the switch and AC is turned on, correct? Implement the derating of the charge and discharge the current if overheated. So all the parameters, there is a all the devices that is integrated, and all the parameters we can give the BMS, and based on our control algorithm that BMS operate. Okay. So you can see overall structure of the battery management system, otherwise the integration of the BMS. So this is your battery pack. So you can see this is the spelling mistake, battery pack. Yeah. So this is your battery pack. Okay. So this is your battery pack, and battery pack is connected with the current sensing. So this is the current sensing, this is a voltage sensing, this is again the current sensing. So multiple current sensings as well as the multiple current sensors are there. Okay. So battery management system, so current measurement, voltage measurement, and temperature measurement. So these three parameters most important part in the BMS. And temperature measurement, so we have to manage the thermal control. Through thermal control we can manage the temperature sensing and temperature sensing. Okay. So these are the integration of the overall BMS. Please remember current, voltage, and temperature. These three parameters are most important parts in the battery management system. Okay. Apart from this parameter, we have to check the humidity of the environment, and as well as the air, because air is not related to battery, but still we have to measure the air because this is a flow of the vehicle, correct? But normally we cannot measure the air because it is not much effect on the battery, correct? It effect on the vehicle, but it not effect on the battery. So that's why we don't care about the air. Yeah. So till now, any confusion for the battery sensing parameter, voltage, current, and temperature, as well as the isolation, as well as the integration of the BMS? Is there any confusion till now? Okay. Now we are going to discuss the example. So numerical of the battery parameters. So based on the battery parameters, we have to find out the SOC, SOH, yeah, maybe the register, yeah, maybe the other components. So first example, so we have a battery pack parameters. We have to calculate the battery pack parameters. So some parameters we have. So battery cell voltage, there is a 3.7 volt because there is a lithium ion battery. So normally nominal battery cell voltage, there is a 3.7 volt. Battery cell capacity, there is a 2500 milliampere, otherwise we can say the 2.5 ampere hours. So normally we can say unit of the battery capacity, there is a ampere hour. So that's why we have to convert from milliampere to ampere hours. Number of cell in the series, so there is a 96. So all cell connected in the series, those are 96. Number of cell in the parallel, there is a 9. So parallel cell combination, there is a 9. Battery pack internal resistor per cell, there is a 50 milliohm. So you can see this is a per cell resistor. Okay, it is a not the overall battery pack register, it is a battery per cell register. There is a 50 milliohm. Average load current, there is a 50 ampere. So load current is a 50 ampere, and battery capacity there is a 2.5 ampere hours. So we have to calculate the parameters. So what type of parameters we have to calculate? So let's see. So calculate the following parameter. So please note down. Otherwise, please remember. So what type of parameter we have to calculate? So we have to calculate the total peak voltage. What is the total peak voltage? There is a battery peak voltage. We have to calculate total battery peak capacity. There is ampere hour. We have to calculate total energy store in watt hour, otherwise the kilowatt hour. Total internal resistor of the pack, voltage drop at load current, terminal voltage under the load, power output under load, and energy delivery time in ideal conditions. So we have to calculate total 8 parameters in this numerical. So from starting from the first part, total peak voltage. So how we can calculate the total peak voltage? Any idea? Any student? Any idea? Total peak voltage.
From number of series connection of cells.
Correct. Total battery peak voltage. So we have to calculate the total battery peak voltage. So V battery, otherwise the V peak, we can say the V peak equal to V peak is equal to how much? 355.2 volt as per my calculation. Correct. So this is the total battery peak voltage. Second parameter we have to calculate the total peak capacity. Total battery peak capacity. So what is the formula for this capacity? So there is a n parallel
6 into 2.5.
into
2.5.
cell, correct? So n parallel there is a 6 and cell there is a 2.5. So cell is 2.5, correct? Yes, cell capacity there is a 2.5. So C peak is equal to 15 ampere hours. Next parameter we have to find out third one, total energy store. Total energy stored, correct? So that is in watt hour. Okay. So total energy store, what is the formula? E equal to, energy is E. E is equal to V peak into I peak. Sorry, otherwise the C peak. So V peak we got 355.2 and C peak we got 15. So E is equal to 355.2 into 15. So 5328 watt hour. correct? So this is the your total energy store. And fourth one there is a total internal register of the pack. Total energy, sorry, total internal
This is
register of pack. Pack, that is a battery pack, okay? For the series and parallel combination, so we can say series register, so R series is equal to 96 into 0.05. Why 0.05? Because internal cell register there is a 0.05. So you can say the internal register 50 milli ohm. So we can convert into ohm. So there is a 0.05 ohm. And cell connected in series there is a 96. So we can say 96 into 0.05. So we will get 4.8 ohm. This is a per sting, okay? Per sting. Because all are connected in the series, so we can see the per sting R series register. And for the 6 sting in parallel, because parallel connection there is a 6. So for the 6 sting, for 6 string, for 6 string, because that sting in the parallel, okay? So for the 6 string in parallel, we can say R total equal to 4.8, yes, 4.8 divided by 6. So R total equal to 4.8 by 6. It means that is like 0.8 ohm. Yes, student, is there any confusion? Then please let me know, because this formula is most important. So how we can calculate the per cell register, series register, parallel register, that's the most important part. Okay. So next one is a voltage drop at load. So fifth one, I think there is a fifth one. Yes, fifth one, voltage drop at load current. Voltage drop at load current. Okay, so we have to measure the voltage drop at load current. So load side, how much voltage drop? So we can say voltage drop, we can write the voltage drop is equal to I into R, I into R. We got I there is a 50 ampere, and R total there is a 0.8. So this is the R total, okay? R total. So V drop is equal to 50 into 0.8, so there is a 40 volt. So this is the voltage drop at the load current, so I into R total. Yes. Next one, terminal voltage under load. So there is a 6. Terminal voltage under load. Under load condition. So we can set the V terminal is equal to V peak voltage, battery voltage minus voltage drop. So V peak we already calculate, there is a 355.2 minus voltage drop. How much voltage drop? There is a 40. So V terminal is equal to 355.2 minus 40. So there is a 315. 0.2 volt. So this is the terminal voltage under the load condition. Second last parameter, there is a power output under load. Power output under load. So power output, P output is equal to V terminal. Power is nothing but P equal to V into I. So V terminal into I. So V terminal we got 315.2 and I, that is I think 50. Yes, I is a 50. So P is equal to 15706 watt. Yes, if there any mistake like calculation mistake, then please let me know. Correct. So I did this numerical previously in my handbook. So if is there any mathematical mistake, then please let me know. Okay. And last one, there is a energy delivery. So last one, there is a energy delivery time. Energy delivery time. Correct. So that is your ideal condition. So time, that is a cell divided by I. So capacity, there is a 15 and current, there is a 50. So energy delivery time, that is your 0.3 hours. Otherwise we can say 0.3 hours, otherwise we can say the 18 minutes. Correct. So these 8 parameters, we have to calculate it. Total battery pack voltage, there is a B pack equal to A series into V cell. Then we have to calculate the total battery pack capacity. There is a ampere hour, so N parallel into the cell. There is a current rating. Then we have to calculate the total energy store. So energy store is nothing but V pack into C pack. Total internal register per cell internal register is given. So we can say the total internal register R series into per cell register. So 96 series series cell into per cell register, there is a 0.05. Then voltage drop at load current. So how much voltage drop at load current? So voltage drop is equal to I into R. So where R is a total register of the circuit. Then terminal voltage under the load. So how much terminal voltage we will get under the load condition? So V peak minus voltage drop. Obvious, whatever is voltage drop, so we have to minus. Then power output under load, so power is nothing but P equal to VI. So V total, otherwise V terminal into the I. And last one, there is a energy delivery the time. So time equal to current rate, cell rating, there is a ampere hours divided by the current. Okay, so there is a 0.3 hours, otherwise the 18 minutes. So is there any confusion, any query for this numerical? Any confusion, any query?
No.
Okay. Second numerical. Second numerical we have to see in the electric vehicle. Electric vehicle use the battery pack consists of the 120 lithium ion cell connected in the 20S6P configuration. Each cell has the following configuration. Nominal voltage, there is a 3.6 volt. Cell capacity 2.5 ampere hours. Maximum charge current 2C. Minimum discharge current 3C. Maximum discharge current 3C. Internal resistor per cell 45 milliohm. And maximum safe temperature, there is a 55 degree centigrade. Correct. So we have to, and BMS is responsible to monitor the voltage and current and temperature, protecting the battery from the overcurrent, undercurrent, and over temperature. Balance cell voltage when the cell voltage difference exceeds the 100 millivolt. So that is managed by the BMS. At certain instant, the following measurements are taken. Peak current, there is a 72 ampere at discharging. Maximum cell voltage, there is a 3.74 volt. Minimum cell voltage, there is a 3.58 volt. Temperature of the fuse cell, there is a 57 degree centigrade. So these are the BMS responsible, and we got some parameter from the BMS. So our task is, question is, what is the total peak voltage at the instant based on the average cell voltage? So there is a first part. Second part, what is the total capacity of the battery pack? There is ampere hour. Does the BMS need to trigger the balancing and justify your answer? Does the BMS need to trigger the over temperature protection? So BMS have to work. So there is that need to operate for the trigger. What is the total internal resistor of the peak? What is the voltage drop due to the internal resistor at 72 ampere? What is the terminal voltage under the load? And is the discharge current within the safe range? So whatever is discharge current is measured by the BMS. Is it safe range? So discharge current, there is a given 72 ampere. So this 72 ampere discharge current, there is a safe for the BMS. So we have to answer to those questions. Okay. So starting with one by one. So any student, so how many series and parallel for this numerical? Any student? For this numerical, how many cells are connected in series and how many cells connected in parallel? Yes, yes, Niroj, are you there?
20 cell series and 6
Six and
parallel.
parallel.
Correct. So based on this numerical, we can get the data from this digit. So 20 S indicate this is a series and P indicate there is a parallel. So we can say series connection, series cell 20 and parallel cell 6. So don't confuse in the exam as well as the maybe in the nameplate. So sometime on the nameplate they mention the series and parallel cell, and sometimes they mention 20X and 6P, this type of combination. Correct? So don't confuse during the your exam in the nameplate. Total the instant so first battery pack voltage. Okay, so battery pack voltage, so we can say the V cell is equal to 3.74 plus 3.58. Why 3.74 and 3.58? So 3.74, that is the measure the maximum cell voltage, and 3.58, there is a minimum cell voltage. There is a measure by the BMS, correct? So BMS measure this parameter. There is a maximum cell voltage and minimum cell voltage. So we have to take the average. So that's why 3.74 and 3.58 divided by 4 divided by 2. So V cell is equal to 3.66 3.66 volt. Okay, so this is your average, correct? So we can say the average cell voltage. So this is also average cell voltage, so total battery pack voltage 20 into 3.6 is why 20, because series connection is a 20. That's why we have to multiply the 20. So 20 into 3.66. So V peak is equal to 73.2 volt. So this is for the first answer. And second one we have to see the battery pack capacity. So battery pack capacity, there is ampere hours. So battery pack capacity, we can say ampere hours is equal to 6, because 6 is connected in the parallel, I think so. Yes, 6 is connected in parallel, into cell capacity. So there is a 2.5. So ampere hours is equal to 15 ampere hours. But we have to find out that is your watt hour. Otherwise we can say yes, ampere hour, that is a sufficient. Otherwise you can say the watt hour. So 73.2 into the 15. So there is a total watt hour, we can say 1098 1098 ampere hour.
What hour?
Watt hour, sorry. 1098 watt hour. Okay. Otherwise maybe you can convert into kilowatt hours, so that is up to you. Okay, there is a battery pack capacity. Next parameter we have to find out, does the BMS need to trigger balancing and justify it. So balancing check. So any comments on this third question? Does the BMS need to trigger the balancing? Any student? Any student want to comments on this question? Does the BMS need to trigger the balancing?
Maybe not, sir. Hello?
Mm-hmm. Yes,
Hello?
yes. You are audible.
Maybe not, sir.
Maybe not. Why?
Mm, I think BMS tries to balance the voltage and current to each cell of the battery, but the cells are already connected in series and parallel. But in case of lithium-ion battery, we use BMS. But in general, for mathematical calculation, uh, I think maybe not.
Okay. Any other student? Any other student want to give the comments? Okay. Okay. So let's see. So third part, balancing check. So first we have to find out the voltage difference, correct? So voltage difference is equal to 3.74 minus 3.58. So why 3.74? There is a maximum and minimum. So maximum voltage range 3.74 and minimum voltage range, that is a 3.58. So that is your difference. So is equal to 0.16 volt. Correct. Otherwise we can say 160 milliwatt. So why we have to convert 160 milliwatt? Because in the question they are mentioning balancing cell voltage when the cell voltage difference exceed the 100 millivolt. So cell voltage difference exceed the 100 millivolt, then BMS is responsible for the cell balancing. So this difference is what? How much? 160 millivolt. So can you now answer the this question?
Yes,
So
sir.
if
It's practical.
yeah, so we need to balance, yeah, no.
Bar. Yes.
Yeah, so now voltage is a 160 millivolt, correct? And in the BMS, they are measuring balance voltage when the cell voltage difference exceed the 100 millivolt. So this voltage difference is a 160 millivolt. So BMS is a trigger, correct? So question is, Does the BMS need to trigger for the balancing? Answer is a yes. And why? So answer is a yes. It is a trigger because there is a voltage difference is a 160 milliwatt and there is a more than the 100 milliwatt. Correct? So we can say yes, cell imbalance greater than 100 millivolt. Correct? So that's why it is a trigger. Otherwise, this difference is below the 100 millivolts, then it is a not trigger. Okay. Fourth one, over temperature protection check. So fourth one is does the BMS need to trigger over temperature protection? Yes. Any other answer? Any student want to give the answer? Does the BMS need to trigger for the over temperature protection? Fourth one, there is over voltage temperature protection. Yes. So maximum allowable temperature there is a 55 degree. Yes. In the question, yeah, maximum safe temperature that is a 55 degree, but in the BMS case, temperature of the fuel cell may be the 57 degree. Correct? So we can note down. So maximum allowable temperature equal to 55 degree. Correct? And measure that BMS measure BMS equal to 57. So what do you think? Yes or no? Over voltage triggering, that is a possible or no?
Yes.
Yes, correct. So there is a yes. Answer is yes. BMS may be BMS must trigger thermal protection. Correct. So we have to trigger the thermal protection. So answer is a yes. Next one, next part. Just one more. Just one minute. So I want to give the charging. Yes. Next part is a fourth one. Yeah, fifth one. What is the total internal register of the pack? Any idea? Per string in the series. In the previous numerical, we already calculate the string register, sorry, series register. So we can say R series, otherwise the string register. So 20 register, there is a series into per cell register, there is a 0.045 ohm. So R series is equal to 0.9 ohm. And what about in the parallel? R parallel 0.9 divide by total cell connected in the parallel. So R parallel is equal to 0.9 divided by 6, 0.15 ohm. So this is your uh, total register. So we can say this is the total register. Because this is your R series divided by R parallel. Correct? So this is your total resistor. There's a 0.15 ohm. Okay. Next we have to calculate the voltage drop at 72 ampere hours. Sorry, 72 ampere. So 6 1 is what is voltage drop due to the internal resistor at 72 ampere. So suppose current rating is 72 ampere. So that time we have to calculate the internal resistor. So 6 1 voltage drop at 72 ampere. Okay. So V drop, voltage drop is equal to I into R. So how much I? So I, that is a 72, and R, in the previously we already calculated R 0.15. Voltage drop is equal to 10.8 volt. So this is your voltage drop. Seventh one, there is your voltage, terminal voltage. Terminal voltage.
Sir,
Yes.
72 ampere is the load current or the battery current? What current?
So in the question is define the load current. Load
Yes,
current.
sir. Yes, sir. Got it.
Next one, that is your terminal voltage. So we have to calculate the terminal voltage. So terminal voltage. So there is a battery voltage minus the voltage drop. So battery voltage minus the voltage drop. So how much battery voltage? There is a 73.2. We calculate the battery voltage. Yeah, 73.2, and voltage drop. There is a 10.8 minus 10
Sir,
point. Yes.
what is the numerical weightage in exam, sir?
Why you are asking now? Why you are asking now?
So, uh,
You don't
many
like
more.
the numerical?
Sorry, sir.
You don't like numerical?
No, sir. No, I like sir numerical. So when numerical become correct, then
You will get the full marks.
yeah, yeah, sir.
Suppose,
So that I am asking you, sir.
so as per the like university rules, so I have to ask to Jitendra sir. In the last semester, Jitendra sir told me, but I forgot now. So suppose is there no rule, then weightage is a 60% and 40%. So 60% is theory and 40% is numerical.
Okay, sir. Okay, sir.
So
Thank you, sir.
it there is a no rules and regulation for the university side, correct? So it is totally depend on me. Then for my side, 60% theory and 40% is a numerical.
Okay, thank you, sir. Thank you.
Okay. So terminal voltage, there is a 72.2 minus 10.8. So we will get the 62.4 volt. So this is your terminal voltage. Last one, last question. Safe discharge current peak. So it is a safe to discharge the battery current peak. So we have to give the commits. We have to write the commits. Safe. Just 1 minute. Safe discharge current check. Yes. Any comments for this question? So that 2C and 3C is given. So here is given somewhere question. Yes. Maximum charge current, there is a 2C, and maximum discharge current, there is a 3C. So is it safe to discharge as well as charge? So question, is the discharge current within the safe range? So any comments? Yes, yeah, no. So safe discharge current. So maximum discharge per cell maximum discharge per cell, that is a 3C. And C, we already calculate 3 into 2.5, correct? So that is up to 6.5, sorry, 7.5. Correct. So there is a maximum discharge per cell. So total safe discharge 6 into 7.5, 45 ampere. So any student now comments for this question. So is it safe to discharge your battery? So current drawn, what is a current drawn and total safe discharge, there is a 45 ampere. So this is the total safe discharge, there is a 45 ampere, and current drawn, there is a 72 amperes. So 72 ampere, there is a current drawn. So in the question is mentioned there is a 72 ampere. So we can say the I mentioned current drawn.
Sir, can you explain the expression 6 times 7.5 again?
Just 1 minute. 6. What this one?
Yes, sir.
Yeah. So 6. Why 6 time? Correct.
Yes, sir.
6 parallel.
6 is parallel. That's why. In parallel, voltage is same. Correct. Current is distributed.
Yes, sir.
And 7.5 there is a current. So we have to take care about the current. And while the current, calculate the current and current in the parallel, that is not the same. It is a distributed and voltage is same. So that's why we have to consider 6. And 6 is your parallel cell. So that's why.
Okay. Okay.
So current drawn from the battery, there is a 72 ampere and total safe discharge, there is a 45 ampere. So can you comment for this question? So overcurrent condition. So suppose in overcurrent condition, so BMS must be disconnected, otherwise a limit charging. But for this case, so total safe discharge there is a 45 ampere, and our charging current there is a 70. So current drawn from the battery there is a 72 ampere. So we can say it is a no need to. So this is a safe charging, safe discharging we can say. So this is the safe discharging current value.
Safe,
Yes. Yes, any confusion, any comments?
sir, it is not the safe discharging, sir.
It is
Not safe.
what I said. I said yes, yeah, no.
No, sir, no.
No, correct? Yeah. So this is the not the safe discharging, correct? So it must be the disconnect, otherwise the limit the charging. So answer is it is a not the safe discharging. Correct? No. Answer is no, correct? Got it? Yeah, still
Yes,
confusion. Got it? Got it? Yes, yeah, no. Please let me know. Got it? Yeah, no.
yes, sir. Yes, sir. Got it.
Okay, good.
Got it.
Good, good, good. So, yeah. So, yes. So, is there any confusion for this numerical? So, first we have to calculate the what is the total battery pack voltage, what is the total capacity of the battery pack, does the BMS need to trigger for the balancing, there is a cell balancing, does the BMS need to trigger, there is over temperature protection, what is the total internal resistor of the pack, what is the voltage drop due to the internal resistors is the 72 ampere, and what is the terminal voltage under the load, and is the discharge current within the safe limit. Is it any confusion? So this type of numerical I will ask in the exam. and every question carry the 1 marks. Correct? Maybe the 1 marks, yeah, maybe the some question, maybe the 0.5 marks. Okay. So key point from the today's class. So battery pack sensing current, voltage, and temperature, isolation and thermal control, and numerical of the battery parameters. From the in the next class, we will discuss the introduction to the fuel cell. So we can say the hydrogen fuel cell, otherwise the proton exchange membrane fuel cell for the e-mobility. Correct. In the next class, we will discuss the these two topics. These are the few references which I use to prepare these lecture notes. And thank you so much for your attention. And if you have any question, any confusion from the today's class, then please let me know. If you have any confusion, any query.
Thank you, sir. Thank you, sir. So thank you.
Okay, no confusion, then we can close the today's class.
Thank you, sir.
Thank you so much. Most welcome.
Thank you, sir. Good night.